Hello, we're going to talk about systems of linear inequalities and equalities today. But we're going to start off with a little warm up because we really need to try to get good at these quadratics. So it says to solve the quadratic, which we know means to get x by itself or to find the zeros or the solutions or the x-intercepts. And we got to think about the different strategies. Um, B is even here, but always the best thing you can always try to do first is factor if possible. It looks like a guy that might be factorable. 1 and negative 15 gives me negative 2. That's not going to work. 3 and negative 5, that gives me negative 2. That's what I need right here. So I can rewrite the left hand by x plus 3 and x minus 5. And if I set that equal to 0, I can use that zero product property because that means this times this equals 0. And if that is the case, one of those two quantities have to equal 0, so x would equal negative 3 and 5. Okay, so that's just the warm up, and now we're going to start talking about those systems. And we're going to look at graphing today. It's going to be the number one thing. First of all, let's look at some lines, though. Remember how to write equations. You'll be given a fact, and sometimes you'll be given two facts or whatever the situation may be. But if it's going to be linear, it's going to have a constant rate of change. That rate of change is going to be very constant, never changes. So for this particular gym, there's initial fee of $15 and then $1 per day. Well, what's the rate of change? The rate that's changing is this. It's going to be at 1 per day. So that will be what we call the slope. And the initial fee is what we're going to call the initial condition. So they want an equation using C and D is for days, and C is for total cost. So the cost is going to have that initial cost, that initial condition of 15 plus $1 per day. Now, usually when we graph, we usually like it in that y equals mx plus b form. So you might want to do some rearranging here to change it to 1d or just d plus 15. But that's how we write that equation. On this healthy gym here, this initial fee is less, but the daily fee is more. So what would it be? Well, the rate of change, the slope will be 2 per day. That per is a big indicator of a rate of change or a slope. So the cost here is going to be $5 plus $2 each day. So if it was 1 day, it was 2. If it's 2 days, 4, and so on. You could rearrange it, like I said, to be 2d plus 5. And that's how we write equations. Well, today we're going to look at two equations at once, just like we were looking at two equations right in this example to talk about systems. Systems are two or more equations that have common variables, the same variables. I use C and D there, but generally we try to use X and Y so that we can have them in a common way that we're used to. Now, I went ahead and threw up a graph here. I was going to have you graph it, but I hate it whenever the scales are different. And 15 is kind of big. I probably would have counted by 5s personally, but then that didn't work out too nicely with the 2 rate of change here. So I just went ahead and threw up a graph here. And I want to know then the solution is what they have in common. So this point where those two graphs is the only point they have in common, that would be called the solution. And what does it represent or mean in the context of our problem? Well, it's the only point that is true for both graphs. But what that means is on day 10, both gyms, I don't know what I'm writing. Both gyms, a little glitchy, cost $25. That would be the cost for 10 days, not on day 10. For a 10-day membership, it would cost $25. That's the only time that they would have the same cost based on membership days. Every other time they will be different. So by the end of this lesson, we're going to be able to solve systems graphically is how we're going to look at it. This classification, it means that we're going to have some vocab, okay? And then we're going to solve systems of inequalities as well. Here's that graph again. I said, what does it tell us? Well, let's look. The orange graph is the healthy gym, and that tells me it has a steeper rate of change. It's growing faster, which means the rate of change is more, which means the daily price is more. This flatter one says initially it costs more. The y-intercept is higher. There's initial, but it will have a lesser slope, and its rate of change would be less. So basically, it cuts the graph into these like two regions before they are equal and after they are equal. And this actually obviously goes forever. So before the break, I call this the break-even point a lot of times. It was better to go to the orange gym because better, it'd be cheaper. So I would go to the healthy gym maybe if I was on vacation. If I'm on vacation, I'm going to join the healthy gym because it's going to save me for money. I don't live there. And I can be 10 days relatively low price compared to the workout gym. But then after that, at that point where they break even, then they switch places. And then from that point on, the workout gym is the better price because it will be a lower total cost. That that rate of change allows it to catch up and switches which linear function is like the better deal. So let's practice. The cost of 10 days at Healthy Gym, which is the orange graph, is, we already discussed that, that's going to be $25. Is that less than, the same as, or more than 10 days at the workout gym? Well, 10 days at the workout gym was also $25, so that would be the same as. Which of the following is true for memberships lasting longer than 10 days? So if it's over 10 days, which gym is better? Well, over 10 days, we want to pay less money. So the blue graph would be better, and that would be the workout gym. More practice. How many solutions will this guy have? X plus y equals 5 and x plus y equals 6. Don't forget, x plus y equals 5 has infinitely many solutions. There are infinitely many points that make that true. The problem is kids like to think of the positive ones. 1 and 4 is 5. 2 and 3 is 5. But what about 1.1 and 3.9? Like, you can keep going to all these decimals. There are infinitely many points, which is why we use a picture to show us the solutions. X plus y equals 5 is the same thing as y equals negative x plus 5. And the graph looks like up 5, down 1 over 1. It's this downward slope line. And all of these points, all these ordered pairs would be combinations that make it true. Now, x plus y equals 6, that also has infinitely many points that make it true. But which ones make them true together? When will they have the same number that equals 5 and 6? Well, that can't happen. Those are no solutions. And the way you can tell a graph has no solutions is when you graph it and you have that x plus y equals 6, and you subtract the x from both sides, you get negative x plus 6. My pen is lagging. This would be parallel. Those lines look parallel because there's no solution. There's no place that those two lines will ever touch. What point approximates the solution to this graph? It looks like it's right about here. We're definitely going to approximate. I could write the equation of the line and figure it out, but by the graph, sometimes graphing is not a very good method. It looks like maybe like 1.1 point, I don't know. What do you guys think? 0.1? Hard to tell. The lines are pretty thick, so you can't quite tell the point of intersection there. But sometimes graphing is not the best method because you can't quite tell exactly where those lines cross. Okay, so here are the vocab words you need to know. There are 3 different possibilities of the way these lines can interact with each other. There could be no solution. We said they could be parallel. If they are parallel, we say that the system is inconsistent. Remember, the prefix in means not, so it's not consistent. And you're usually looking for a solution, so that kind of helps me know solution, non-consistent, inconsistent. Now, this one is consistent. They could touch. And they touch in one point, just like we would expect most of them. And we call that consistent because what we are looking for. We are looking for solutions after all. It is consistent. Independent. What does independent mean to you? Well, it means that you're on your own. You could be by yourself. And it's because there are 2 separate lines. I have had texts that call this inconsistent and independent as well because there are 2 separate lines here. Now, in this particular example, the lines actually could be right on top of each other in case they touch everywhere. And we say there are infinitely many solutions. Those lines coincide. So there are solutions because that is what we're looking for, is we're looking for a solution. So it is consistent, but they're dependent because the lines are the same. One line is on top of the other, kind of dependent on each other, if you will. Okay, so those are the vocab words you're going to need when you classify. Kids, do forget those. You might want to put them in a handy place before test or quiz time. So let's practice. Now, the The object is to practice by graphing. We're dealing with lines, and lines are easy to graph, but the video did go through tables. I don't know exactly why. I would not have used the tables. I did stick the tables here for you to use, but I think you should probably just graph by getting y by itself and graphing. So that's what I'm going to suggest that you do. I'm going to just make an itty bitty small grid here because my pen has been acting up. And this first one is super easy to graph. Y is x minus 4. I'm going to go down 4, and that is my y-intercept. And from there, I'm going to do my slope, which is in front of the x. I'm going to rise 1, run 1. I could do that all day if I want. I'm actually just going to leave a dotted line again because my pen is just not cooperating very well. If I had a straight edge, I would connect it at the end of your lanyard. I guess I can, let's see what I can do here. That's not too bad. Not too bad. Okay. But I'm a little wary of the glitching. Now, how about this guy? I got to get y by itself. So let's move the 2x. So I negative 2y, and I'll move it by subtraction, negative 2x plus 8, and divide all the friends by negative 2. And I get y equals x minus 4. Oh, wait, x minus 4, that's the line I just graphed, which would mean that these guys would be dependent graphs because it would be the same thing. They would be touching everywhere, so I can graph, but I can't write, apparently. And we are going to say there are infinitely many solutions. This is ridiculous. Look at that. Maybe it's better over here. Yeah, it might be a dead spot in my board, my slate. Okay, so you don't even have to, the lines would be the same. Oh my gosh, what am I doing? The lines would be the same. Now, in the table, if you did this, you could see this as well, but the table shows 3 of the solutions. The picture shows all of the solutions. So there can't be more than one place of intersection unless it's infinitely many, though. If you plug negative 2 in here, negative 2 minus 4 is negative 6. If you plug negative 2 into here, you would get 2 times negative 2 minus 2y equals 8. Yeah, I think it's my slate has a little bad spot. That's sad. So that would be negative 4 minus 2y is negative 8, is positive 8, excuse me. Add 4, negative 2y is 12, and that is negative 6 as well. So there's one point in common. Plug in the 0, you get negative 4. Plug in 0 here for x, and you get negative 2y is 8, which is also negative 4. You can't have more than one solution without it being infinitely many. So maybe a table is a way to help you find that if you want, but I prefer the graphing. Okay, now I've never seen this before. Infinitely many solutions. I always just wrote infinitely many solutions. They're saying another way you can write it is the solution is forehead, nose, and chin. That's the set of all. The set of all x and y. The big long line means such that this equation is true. So basically what they're saying is there's only one way to write slope intercept. So it says there's only one way to write slope intercept, and that's why I'm changing this now that I think about it. I couldn't understand that, but there's only one way to write slope intercept. So if you write it there, and there's multiple ways to write standard form, point slope form, all those other things. If it can be simplified to this version, then that will be a solution to this particular system. So if you're infinitely many, that might look that way, but you can just write infinitely many for me. So which equations compare with this guy to make it consistent and independent? Remember, independent means separate, so it cannot be the same. So we want one solution, not infinitely many. Well, would this be, basically you just need something different than that, and with a different slope. So we need a different equation. That way it won't be on top of each other. And we would need a different slope so that it wouldn't be parallel. And that makes it consistent. So let's get y by itself here. That would be x plus 2 equals 3y. I don't really even need to finish. It's definitely going to be different, and the slope is 1/3. So that would work. How about y is negative 3x minus 2? Sure, the slopes are different. It's not the same. Works. Y is 3x plus 2. Well, this case, they will be parallel. If 3x plus 2, they'll be parallel. So yes, they would be independent, but they would not be consistent. So that's not a choice. On this one, it looks like they multiplied everything by 2. If you divide everything by 2, it would be 3x minus y equals 4. Let's get y over here. That'd be 3x minus 4 equals y. And that looks okay to me. Did I divide everything by 2? I did not. 3x minus y equals 2. I've got to divide all those pieces by 2 because they have a 2 in common. Now if I get y by itself, it would be 3x minus 2 equals y. And while it looks different, it looks independent, it's not, because when you simplify it, it gets you back there. So that is actually a consistent dependent, so that's not it. And to try this last one, if we get y all by itself, we would have 3y is x minus 2, and then you would divide all the friends by 3. And yeah, that one would work as well. So there's 3 different things you could do to get solutions. There are actually infinitely many equations that you could write that would touch that. And there are infinitely many you could write that would be parallel to it as well, but that's just the vocab. So what happens with inequalities? Inequalities are the same as graphing lines, but there's shading involved. And a lot of times we use at least 2 different writing utensils or types of shading here to help you see the intersections. So what is the graph of the system? So if you look at them both at the same time, of y is less than and equal to this guy and less than this guy. Well, 3x plus 4, which graph is the 3x plus 4? We're looking at the orange graph here. If it's less than or equal, it has to have a solid line. Well, this one has a solid line. Well, they all have a solid line. And it's going to be shaded below or less than. So this graph is shaded above. That is not it. This one is shaded above, also not it. This one is shaded below, but for some reason they stopped here. So why did they stop? Well, because y is less than 3x minus 2 has the dashed line is graphed here. It is shaded below. All of these are shaded below. So all of these have this graph correctly, but the solutions, so I can speak, the solution set is what they have in common. So while this goes, the orange graph goes all the way under, the green graph only is under this line. So the points that they have in common are what is the solution set. So this is at this solid dark line with the dashes. So C is the correct version if the green is the solution set. So where is the solution set? I just showed you. Maybe I jumped the gun a little bit. We're looking at this green zone. And I want you to remember, there are infinitely many solutions to the orange. The orange graph, all those points are solutions. All of these points are solutions, and all of these are solutions. The second graph also has infinitely many. While it's not on the boundary line itself, all of these points in the region of green make it true. But the ones that make both of them true are only in this shaded green area. Obviously, the graph goes on forever. So is 0, -2 in that point? 0, -2 is on the dashed line. That will not make both graphs true. Will 5, 0? Yeah. 5, 0, it's going by 2's, will make both graphs true. Think about it. This says y is 3x plus 4. Yours didn't graph very well. And y is 3x minus 2. If you plug in 5 for x, 15 plus 4, it doesn't say equal at all. It does say equal, and it's not supposed to. It's supposed to say less than or equal. If you plug in 5, 15 plus 4 is 19. 19 is less than 0, so that's true. And this one is just supposed to say a less than and not equal. Plug in that 5, 15 minus 2 is 13. 13 is also greater than 0, so that is a solution. Now, 3, 13 is trickier because it's off the charts. Where is it? Well, let's see if it is a solution or not. Just plug in the x and y into both equations because it has to be true for both equations. 3 times 3 is 9. 9 plus 4 is 13. Is 13 less than or equal to 13? Well, yeah. So this is a solution to the orange graph. Check. Now you got to check the green graph. Plug in x is 3. 3 times 3 is 9. 9 minus 2 is 7. Is 7 greater than 13? No, it won't be true for the green graph. Basically, this will be right on the orange line, but it won't be true for the green graph. So the only solution that is in that green region is 5, 0. So these are the ways that the different solution sets could look like. You could have a case where you're above one line and below the other and they don't interact at all, and we're going to call that no solution. If it's above the blue graph and under the orange, then they would just have this parallel strip in common right in the middle, or potentially just on one side of one line. And then you'll have situations too which I can't believe they didn't draw pictures of. If the graphs cross, you could be under one and above the other. So then it would only have this point here in common. Sometimes we use pencil and pen to see where the overlap or highlighters. If we had those two lines again, and we had above one and below the other, then this would be the region that they overlap. And it could be in any one of those four squares. So let's try this. What is the solution to this system? X plus y is greater than equal to 5 and less than equal to 5. Well, let's just use our brain for a minute. These equations look the same. The only thing different is this sign here. So what could be true? Well, can you be greater than and less than at the same time? No, but you can be equal to. So if I graph these, one's going to be shaded above, one's going to be shaded below. It's going to be the same line, but it will be solid. So actually, the only thing true will be the points on the line. Giselle has a job at a grocery store. We're going to try it with a word problem. It pays $12 an hour. Looks like a rate of change to me. Good indicator of a slope. And a job at the library that pays $9 an hour. Another slope, looks like. She wants to earn at least $135. So she wants to make at least this much money a week, but she wants to work less than 15 hours. The system of linear inequality shown represents the situation. What does the solution represent? Okay, so let's think about this. So there's a rate. This is actually what we call a linear combination problem, where there's two facts and we're trying to write two equations based on it. So if you get 12 at the library, let's call that 12 for each hour at the library. So it's like a rate for the library plus a different job. Oh, I did it wrong. The store. Store is 12. Well, it doesn't matter because I used X. 12 for the store plus 9 for the library, which we'll call Y. She wants that amount of money to be at least 135. She wants that greater than equal to 135. But X is how long she works at the store, and Y is how long she works at the library. She wants that to be less than or equal to 15. Nope, just less than total. So we can graph that by getting Y by itself. Let's subtract 12x. I'm going to move up here. 9y greater than or equal to negative 12x plus 135 and divide everybody by 9. I'll get y greater than or equal to negative 4/3 x plus 15. So the first graph will look like that. The second one, if I get y all by itself, it's pretty easy. Negative x plus 15. So they both have the same y-intercept. We're just going to graph in quadrant 1 here if you're okay. Let's go by 3 since the rate of change here is 3s. 3, 3. So it's 3, 6, 9, 12. Okay. Probably could have gone by ones. That's fine. We'll make it work. So what do we got here? Up 15. 3, 6, 9, 12, 15. The slope is negative 4/3. So I'm going to go down 4. So there's down 3. Down 4 over 3, which is one step. Down 4 over 3. So here. When will I run out? Down 4. Let's plug in 0 for y. And we would get 11.25, it looks like. Might have not graphed that right before. Is this supposed to be solid? This is supposed to be solid. There, about like that. How about that? Okay. And it's greater than that. So this is the region where she'll make more money, up here. But also, x has to be less than negative y plus 15. So you're going to go up 15. Let's do a different color. And this time you're going to go down 1 over 1. So we can go down 3 over 3. down 3 over 3, and I did a really bad job graphing. Because you can barely see the solution set. And it has to be less than that, so that's going to be under the graph. So what do they have in common? Well, that place they have in common with Mrs. Bruno shady bad graph here is right in that region. Okay, so what points lie there? Let's see if there is a picture for it. Oh, there's not. Let's go back here. So let's look. Mrs. Bruno, come on. Looks like she can work. What would be in this? What was X? X is hours at the store. Looks like she needs to work more than like 11 hours at the store, probably. She probably needs to work like 12 hours at the store. Let's see if that would work. 12 hours at the store. That would be 12 plus 3. Well, 12 hours at the store and 2 at the library. 12 and 2 is less than 14. 12 times 12 is 144. 9 times 2 is 18. Yeah, that would be greater than 135. So 12 and 2 would be a solution. Okay, there's other solutions in there as well, like partial hours and stuff, but my graph is so bad you can't see. I probably should have just gone by ones. You can forgive me. So these are the things we talked about today. There's that vocab. You might want to make sure your notes are in good shape. There's different ways the graphs could look. And this is types of problems, classifying, determining if it's a solution, and graphing. And basically, we covered everything we said we were going to do.